Keyword arguments are typically defined as a method for passing optional parameters without strictly predefining them in a function signature. In this standard code block, we define a function using the double asterisk syntax and call it with two named arguments, a and b. Behind this syntax, the machine is executing a specific mechanical sequence to move data from the caller into the function's local scope. We need to see the physical memory operations that occur when these named arguments are processed by the interpreter. We'll move through the Python syntax, read the generated bytecode, watch the CPython stack machine, and track the C-level memory allocations. This internal sequence provides the underlying routing infrastructure that allows modern web frameworks to process incoming HTTP requests. Understanding how Python bridges these external inputs into internal memory is the prerequisite for understanding how massive web APIs operate at scale. At the moment of the function call, Python isolates the argument names from the values being passed in. The compiler translates this call into a series of bytecode instructions, specifically the call function kw opcode. Call function kw informs the stack machine that the incoming data includes keyword-based inputs that must be handled differently than positional arguments. CPython uses a stack machine to organize the call. It pushes the function object, the values 10 and 20, and a tuple containing the string names a and b into a vertical memory structure. This is the exact state of the stack microseconds before the core function logic begins. The stack then collapses. Python binds the name tuple to the values and constructs a single dictionary object on the heap containing the keys a and b. The ..kwargs parameter is a standard dictionary, dynamically allocated at runtime to hold the results of the stack collapse. Once the dictionary is built, it must pass from the high-level Python stack into the C-level execution layer. The CPython uses a receiver function called pyObjectCall. It accepts the target function and the newly created dictionary as direct C-level parameters. As the function starts, Python creates a local frame, where the label kwargs points directly to that dictionary in memory. The function logic then executes, pulling data from this dictionary as needed. This dictionary handoff at the C level acts as a boundary, allowing the function to remain isolated from the specific structure of the external inputs. This memory mechanic allows web frameworks to map network traffic to Python code. An HTTP GET request for /user/lulit enters the server as an unstructured string of data. Flask intercepts the string, compares it against your defined routes, and extracts the variable value lulit. Flask then triggers the same dictionary construction process we saw earlier, pairing the route parameter name with the value lulet. This dictionary is passed directly into the Python function you wrote to handle the user route. The function receives a clean Python dictionary, meaning your logic never has to interact with the raw HTTP protocol or URL parsing. Advanced frameworks maintain this same internal flow while adding layers of data verification. Consider a FastAPI request with multiple query parameters, a name and a numerical age. Before the dictionary is finalized, FastAPI runs a validation sweep to ensure the incoming data matches your defined types. It converts the raw string 25 into a proper integer, preparing the data for the function call. Only after validation is the final dictionary structure committed to memory. This validated dictionary is passed through the same pyObjectCall architecture used by basic Python functions. Regardless of the framework's complexity, the final delivery of data relies on this dictionary handoff at the execution layer. We can see this universal rule by attempting to use keyword arguments with a function that isn't designed for them, such as print BMI equals 25. Python still builds the kwargs dictionary, creating the key BMI and the value 25 in memory. This dictionary encounters the C-level constraints of built-in print, which only allows specific keys like sep or end. Because BMI is rejected, it triggers a type error. This confirms dictionary construction is a universal step in the call process, even if the target function is too rigid to accept the result. This creates a mental model for how high-scale Python systems are designed. Raw, unpredictable internet data enters through a network framework. That data is converted into a standard dictionary and bound to a function's memory frame. Keyword arguments function as a dynamic interface pattern, decoupling the external request from the internal execution. The dictionary mechanism is the bridge that allows a highly structured function to securely execute against variable, external data.